What's up? What's up? What's up? What's up? What's up? What's up, Sci Fam? It's another science notebook page with your boy Nickel here. And today we're going to look at Newton's third law of motion. So go ahead and put your title on your page that says Newton's third law of motion. We will define it. We'll also look at some other things like we did in the second law of motion that will help enhance our definition and understand it better, like the law of conservation of energy and friction. And then we'll do some examples at the bottom of our page. So let's begin. Newton's third law of motion is the final of his famous laws of motion. And what Isaac Newton observed was that when an object, we'll call that object A, when object A exerts a force, a push or a pull, when object A exerts a force on object, we'll call this one object B. Well, this object B is going to exert, a force back on object A. So when object A exerts a force on object B, B exerts a force back on object A. But these forces that are being applied to one another from A to B and from B to A have two properties. First off is that they're actually equal in force, but they are opposite in direction. So let's think about this for a second. If somebody were to go up to a wall, and a very easy idea here for us to just visualize is if you were to go up to a wall and punch the wall, you're not just going to put your fist through the wall. It doesn't quite work like that. You don't just break a hole through the wall. That doesn't happen. Instead, the wall is going to exert a force back on you. The harder you punch the wall, the harder the wall pushes back on you when you punch it. So when A exerts a force on B, B exerts a force back on A. Now the same thing is true if you've ever stubbed your toe before. You accidentally kicked the coffee table in your living room, and that coffee table in your living room kicked you back. So this is just a summary. We'll dig in a little deeper. To understand this idea that one thing is going to affect another, and when A puts a force on B, that B puts a force back on A at the same time, that's equal and opposite, it allows us to uncover this law that's in physics. But it really ripples into our lives and throughout. And this is the law of conservation. I'm sure you've heard the word conservation before. If you want to conserve something, you want to save it, meaning that it's reused. Law of conservation, but this time we're talking about of energy. These are cursive, and this is of, and this is cursive, and this is of, if you can't read that. So it says law of conservation of energy. And the law of conservation of energy states that energy, remember that thing that we defined way back when, a few science notebook pages ago, the measurement of an object's ability to perform work. These are things like motion and light, electrical fields, magnetic fields, sound, and even thermal energy. Energy, those types of energy, they cannot be created and they can't be destroyed. So you can't just get energy out of nowhere, and you can't just get rid of it. It's only going to be transferred from one form into another form. So a very, very famous example of this is something that was named after Isaac Newton. This is called Newton's Cradle. And this is a gift that I got from Google Images, where you can see that if you raise one of the spheres up into the air and you build up the potential energy in that sphere, when it then is released, that potential energy is transferred from potential into another form, into kinetic. It then hits the next sphere. The energy is transferred between the spheres until it hits the last one, and the last one has nowhere for it to transfer to, so therefore it flies up into the air. So if we were to draw this, we have our first sphere, and it's coming in to contact with the next ones. So as this one comes in, it's coming in hot, with a lot of force. It then is transferred from one to the next, and the last sphere is going to get all of this energy. And I didn't draw my arrow very accurately here because the energy that it's going to get is going to be equal to the energy that went into it, because energy cannot be destroyed. So it's going to then accelerate and fly forward, and this last one then would end up flying up here. And what's going to happen then is it's going to build up that potential energy as it rises, and then that potential energy will turn back into kinetic, and then it will come back. It will then transfer the energy between these spheres until that energy then is released into the next one, and it goes back and forth and back and forth. And since these are hanging from this, these little things here, these, I don't know what to call them, these bars here, there's hardly any friction or loss of energy. And so this goes back and forth because the energy is transferred in a really efficient way. It's not really lost. When we lose energy, and it's not lost, it's not destroyed, it just gets transferred into somewhere else, that's something that's a different vocabulary term, and we call that vocabulary term friction. So we will define that here in 1 second. But first, I like to take this moment to explain this picture, because this is something I love to talk about when I talk about the law of conservation of energy, is that energy, if you are going to apply energy to something, that energy is transferred from one object to the next, to the next, to the next, to the next. And you have to be careful, because sometimes in life, everything is connected, and that energy that you put out just might end up coming back your way. So if you think about putting out positive energy, then positive energy is going to come back and fall on you. If you put out negative energy, then most likely, you know what's coming back your way? Negative energy. A little life lesson with nickel. Anyway, let's define friction. Because friction is a type of interaction between objects that might make it appear as though energy is being destroyed, because an object in motion begins to slow down and stop. But its motion energy is actually just transferred into a different place, usually through friction. So friction is the force between two surfaces that prevents slipping and sliding. So things that have very low friction are things that you slip and slide on, like ice or snow. Things with a lot of friction are going to prevent slipping and sliding. So that's why, for example, you wear cleats when you are playing sports. So you can move really fast without your feet slipping. You get a direct transfer of your energy into the ground without there being slipping. So friction can be really helpful, and sometimes it can be a challenge as well. Like if you were to run and slide across your grass thinking that it was a slip and slide and it wasn't wet, there'd be a lot of friction, and that wouldn't feel very good. So let's draw ourselves a little picture here. Let's draw some grass. So maybe even give it some texture, because if something is really textured, it means that it's going to end up having more friction, things that are textured. So if we have a ball that's rolling here on the grass, I'm going to draw some motion lines to show that it's in motion. Well, over time, as it moves, as Newton's first law of motion says, an object in motion will remain in motion unless acted upon by an outside force. In this example, the outside force is friction, and so this ball is going to eventually come to a stop. So what happened is that this rolling motion is hitting these blades of grass, and these blades of grass are absorbing some of the energy out of this sphere until all of the energy has gone into those blades of grass. So sometimes friction can make it appear as though energy has been lost out of a system, but it's just being transferred. Friction allows a transfer of energy. So let's now explain some third law of motion examples. For every action, there's an equal and opposite reaction, is a good way to summarize Newton's third law. So to begin with, let's imagine that we have somebody that is digging their heels into the ground, but they're pulling on a rope. Let's use this for the rope. Here's our rope. And let's say the rope is attached to a brick wall. So when this person is pulling on the rope, they are applying a force to the rope in the manner of a pull. So if we say that this person is pulling, they're pulling in this direction. And let's say that they are pulling with 500 newtons. Well, they're not moving. So based on what we've learned about free body diagrams so far, we know there must be some phantom force that is in the opposite direction, because this person right here is not moving. They're trying so hard, but they're not moving, which means that this brick wall is actually applying a force in the opposite direction that is also 500 newtons. If this wall was unable to apply a force in the opposite direction of 500 newtons, if it couldn't apply that force, and it could only, let's say, apply maybe a force of 400 newtons, then what would end up happening is we would have motion, like you all know, because we would add up these arrows and we would see there's actually an extra 100 newtons in this direction, and this brick wall would crumble to the ground. But that's not what's happening here. Instead, we have a balanced system. So we're going to have this showing that this person is just tugging on the wall, and the wall is applying an equal force, 500 newtons, in the opposite direction. Now, another way to think about this, because maybe that's tough for you to imagine that the wall is actually applying a force, is if we were to replace that wall, we would have to draw a person here that's digging those heels into the ground and resisting that force, pulling on the rope. And you can imagine then a tug of war. Imagine tug of war where nobody is moving. What that means is that both parties here, both sides, are applying a force that is equal and opposite. So I need to make sure that these arrows are equal and opposite, and this would show that there is no motion. So again, if we use the same example, let's say this guy is pulling with 500 newtons, and this girl over here is pulling with 500 newtons in the opposite direction, and this tug of war rope is not moving at all. So both of these are same situations. If we were to replace the brick wall with a person here, they would have to apply the force in the opposite direction. But here the brick wall is applying that force, even though we can't see the brick wall straining and struggling. So let's think about this in another example of something that actually might be in motion. So let's imagine that we have ourselves let's say it's a UPS truck here, or it could be FedEx or whatever. Amazon Prime delivery, whatever, no bias. It's driving down the road, moving along, and ahead of it is the little go-kart bug thingy, and we'll say that this thing is like a turtle shell on wheels, basically. Now, let's imagine that they're not following the rules of the road, and we'll say that this vehicle, this shipping vehicle, is moving forward to the right at 10 newtons of force. We will say then that this turtle shell vehicle thingy is moving in the opposite direction, head-on collision, but is traveling, it's hard to see that, but this one's traveling at 2 newtons. Well, when these two things then interact with each other, aka we would say that they collide with each other. I'm going to draw it again here. Maybe I'll even draw that there's a little bit of a crunch here in the hood, and give it some wheels because it's rolling down the road, and it has hit the turtle shell vehicle. Well, now in this system, this turtle shell vehicle was traveling 2 newtons in the opposite direction as the vehicle. The vehicle isn't going to just move as though that thing was not even there. So instead of it continuing ahead with 10 newtons of force, 2 of the newtons of force were removed from that 10. So now if we do the math, we would take the 10 newtons of force that it was traveling forward at, and we would subtract the 2 newtons of force that were coming in the opposite direction, and we would end up with this object traveling ahead at 8 newtons of force. So you can see that if there's a collision, the forces that are involved matter. That object A exerts a force on object B, but object B exerts a force back on object A. The object A exerts a force on object B, but object B exerts a force back on object A. So let's look at some GIFs here, or GIFs, or whatever you want to call them. So let's say that this guy here, this professor, he is in this car that has wheels. So that means that there's almost no friction because the wheels are on that concrete and it's really reducing the friction. So if he's holding a mass and he throws the mass forward, that mass moving forward then actually pushes him backwards as well, and it applies a force that's back on him. If we think about this in terms of some type of giant artillery launcher, the artillery launcher is launching this round of ammo in that direction. As it launches it forward, as the ammo leaves and moves in that direction, it also applies a backwards force that's back on the ground, and we can see all of that energy as the dust flies up into the air. So you can get an idea how we don't just interact with the world in a one-way direction, that the world reacts back to us because of the law of conservation of energy, but it all relates back to Newton's third law of motion. And when one object exerts a force on another object, that second object exerts an equal and opposite force back on the first object. The last thing I want to do here is to organize our page like we did in the Newton's second law of motion. And since this stuff is all extra stuff to kind of enhance our definition, let's go ahead and draw a box around law of conservation of energy and friction to show that those are enhancers to our definition, but they are not the definition necessarily by themselves of Newton's third law of motion. So we have the definition at the top, the examples at the bottom, and some enhancement there in the middle. Now you know Newton's third law of motion.